All right, we now introduce something called the antiderivative. So we'll get to that in just a second, but let's start off with an example to kind of work our way through how this works. So remember, if we have the position function, we can take the derivative to get the velocity function, right? The rate of change of position is velocity. The rate of change of velocity is acceleration. So we have a series of derivatives that we can interpret about a physics problem, right? Position, velocity, acceleration. Well, if you know any of these functions, your position, your velocity, or your acceleration, finding any of the functions below it in this list is easy to do, right? You just take the derivative. That's no problem. What if, like in this case, we know the velocity, but we don't know the position and the acceleration? Well, like we already mentioned, the acceleration is going to be easy to find because when we take the derivative, we just get x. So we already know that f prime of x is going to be equal to x because when we bring the 2 down, 2 times 1/2 is 1. We get 1x to the 1, which is really just x, right? So that wasn't hard to do, but what if we want to figure out this position function up here? Well, a couple things. Notice how I'm calling it capital F. That's pretty standard anytime you're dealing with calculus. If you have a lowercase function and an uppercase function and they have the same letter, that means that the uppercase function is the antiderivative of the lowercase function. So we have this notation when we're taking derivatives. We just start putting these tally markers up here to denote which derivative it is. If you're going the other direction, then we make it a capital F to signify that that is the antiderivative, okay? Now, here's the thing. The antiderivative is just what you get by reversing your derivative rule. So since this is a polynomial, we would just think backwards. Just think of it as reverse engineering. We're going to reverse engineer the way that we get a derivative in order to take the antiderivative. So what did we do when we took the derivative here? You bring the exponent down and multiply, and then you decrease the exponent by 1. So in mathematics, there's what's called the shoes and socks principle, which is that the inverse of series of steps is you invert each step and you do them in the opposite direction, right? So it's like shoes and socks. In the morning, you put on socks, then you put on shoes. At the end of the day, you do the opposite of each of those and in the different order. You first have to take the shoes off, then you have to take the socks off. If you have on shoes and socks, you can't take your socks off first and then take your shoes off, right? That doesn't work. Now, whenever you're finding a derivative or an antiderivative, it's nice to just double check it by doing the reverse order. So here we have what we believe is our antiderivative. So x cubed divided by 6. What if I took the derivative? So I'd bring the 3 down. 3 over 6 would be 1/2. I would decrease the exponent by 1 to get x squared, and that is in fact our original function. So we can be pretty confident with the way we went through and found our antiderivative. Okay, but there's a problem here. We haven't quite found the antiderivative yet. So let's take a look at our graphs. So here's the functions. Here's some functions. So here's x cubed over 6. So we've got some different functions that are being displayed here. And they're all versions of x cubed over 6 plus or minus some value, plus or minus some constant. All of these are identical. They're just being shifted up and down. But let's think about this for a minute. All of these functions are going to have identical tangent lines for a given x value, right? Look at x equals 0. Our tangent lines for all 4 of these would be the same. What about at x equals 2? Tangent lines the same. X equals -2. Tangent lines all the same. In fact, at any value you want, at any x value, the tangent lines for all of these graphs will be exactly the same. Well, if the derivative gives us the slope of the tangent line, then it would stand to reason that all 4 of these functions have the same derivative. Okay, so if you have a series of functions and they're all just vertical translations of each other, they all have the same derivative. Well, if that's the case, if they all have the same derivative, how do we know that the one we just found is the right one? All right, so it turns out there's a problem here. All of these functions, the one that we found and claimed to be the antiderivative, x cubed over 6, has derivative 1/2 x squared. What about x cubed over 6 plus 3? Well, that has derivative 1/2 x squared. What about x cubed over 6 minus pi halves? That also has derivative 1/2 x squared. So how are we so sure that this first one is the one that we wanted? And the answer is we aren't. It turns out that any function that differs from x cubed over 6 by a constant by either adding or subtracting a constant number will all have that same derivative. So our answer is not correct up here yet, where we wrote x cubed over 6. We have to represent all possibilities that could be the derivative. So the way we do that is that we take the function we just found and we add a plus c on the end. That c is standing for any possible constant. It could be pi, it could be 3, it could be negative e, it could be 7 squared, right? Think about it, it's square root of 2 over 3. Any value, those are all going to give us this derivative. So what you want to realize is that the antiderivative is really a family of functions. There is an infinite number of functions that fit this form, and if we take the derivative of any of them, they will give us 1/2 x squared. Okay, so that's just kind of a difficulty we have to deal with. What if we really wanted to pin it down and find out exactly which one f of x is, capital F of x is? Sometimes we can do that, sometimes we won't. Sometimes we won't even care about finding the exact one. Sometimes we will. Just depends on what we're doing with the problem. So what we could do, so if we are given additional information, then we can go through and figure out exactly which of those infinite number of functions is the exact one that has the derivative for the one that we're looking at. I mean, they all have the right derivative, but we want to know which is the right problem for the problem that we're working on, the thing that we're trying to figure out. So what if we also knew that our antiderivative passed through 1, 1, the point 1, 1, right? Could we use that additional information to go through and get this figured out? Could we use that additional information to go through and figure out exactly what our value is for c? So we're going to take the function that we've been dealing with, x cubed over 6 plus c, and basically what we're going to do is we're going to rewrite that with our values, the x and y values that were given from the point, the additional information, and we're going to plug that in. So here's my x, here's my function output or my y value. We plug them right into the equation, and then we solve for c. So if I go through and solve for c, I'm going to end up with c is equal to 5/6, right? Because you're going to end up with 1 minus 1/6 over here, so you end up with 5/6. And then you just put the whole thing together into your function, and now we know that capital F of x should be equal to x cubed over 6 plus 5/6. And what if we go back to our graph over here and we actually see this, and it turns out that, yep, this black one right here is in fact the one that we were looking for. That's the value that actually fits our problem. Any of these would satisfy the derivative requirement, but we needed extra information to go through and figure out which one is the actual position function. Okay, so that's something you have to be aware of. That plus c is an easy thing to forget. Just get in the practice of putting that plus c on the problems and then realizing that sometimes you're going to have to actually solve for that plus c. So sometimes they're just going to say, find the antiderivative. You work through the derivative backwards and you slap a plus c on the end and you're done. Sometimes they're going to give you additional information. Oftentimes it will be in the form of a point. So they'll either tell you the input and output values, right? Maybe with units or something like that, or they'll specifically say the graph goes through this point. But it's the same thing. It's an XY pair being given to you. You'll plug it in the same way that I did. You'll solve for C, and then you'll finish the problem.